Welcome. We're going to start the chapter 13, which is surfactants at this point. We'll begin with a simple demo about surface tension in soap. Now, the book had wanted me to try to use a tack. I could not find a tack, so I found a candle wick, which serves just the same. Okay, I'm going to attempt to show the magic of surface tension. That little candle wick right there, it's floating on top of the surface. Dip this as much as I want. It's not going to change anything. This around, dip this in. Try as I might, we'll see. Nope, won't stay up anymore because of the detergent. Try one more time. Nope, won't stay up. Now, one of the first things we need to consider here is density, as we do with this chapter. Density is of a substance is its mass per unit volume. Density is stated in units of grams per milliliter or grams per cubic centimeter. Now, don't confuse density with weight. Something can be heavy and not very dense. A tree is very heavy and will crush you, but a tree can float on water, like a big log can float on water because it's not quite as dense. A block of lead is incredibly dense. Density is simply calculated mass over volume. We're not going to really worry about that so much, but know that you will be able to calculate that. Everything floats on water so long as the density is less than that of water, which is typically 1 gram per centimeter cube. Anything that is smaller density will float. Anything that is heavier will sink. Now, boats float on water, not because they're less dense, the material on them is less dense, more that the volume displaced is larger than essentially the mass ratio. That when you build the boat, you displace a lot of mass, you displace a lot of air in the empty hole, and that volume that's filled with air averages out the density, so a boat is actually much lighter than you would expect. That's why you can get a big steel boat floated on water, because it's displacing a lot of air, water as air. Soap typically floats on water because of the microscopic air bubbles that are whipped into it. Ducks float on water because they have a oil in their feathers that traps air close to their body, so it helps them float and prevents also their feathers from wetting properly. Now, in the demo, the wick should sink. It is heavier than the water, but it's held aloft by something called surface tension. The surface tension supports both insects as they land on water and the wick. That's because the water on the surface is different from the water in the interior. When we looked at changes in liquids in the last chapter, was water evaporated from the surface, but when it boiled, it could boil from any point that had enough energy. But the surface water, it starts to evaporate because in the interior, the water is equally attracted from all sides. It's essentially bouncing around and bumps into materials left, right, up, down, front, and back. And so it's equally chained in place. And so while it's sloshing over each other, they're all kind of supporting each other. but the water molecules on the surface are only supported on the sides and below. There's no support on the top. So they can easily escape that way, but when something pushes down, something with opposing force pushing down, the water will stick together and push back. There's a strong cohesive force that will push back if something is light enough. And this cohesive force is what's responsible for the surface tension. Now, this will be able to fight back against gravity or like just very light things pushing. If it becomes too heavy, it will force the water molecules out of the way and sink. But if it's light enough, the water will provide a force pushing upwards and help it float. Now, anything that will break up this surface tension will cause the object to sink, because lower surface tension means it provides less of a buoyant force pushing the object up. So one way you can kill insects in the summer is having soapy sugar water. If you put a little bit of sugar in water, the insects will become to drink. However, the soap will destroy the surface tension. So if they try to land on the surface of the water, they will sink in and die. However, be careful. You can kill plenty of pests, but you can also kill plenty of good insects like bees and butterflies that maybe you less want to kill. The main thing we're going to study in this chapter are detergents and soaps. Detergent is Latin for deterge, which means to wipe off or to clean. The earliest known soaps were, it's thought that the Babylonians knew about soap so that'd be about 5,000 years ago. That early Phoenicians and early Egyptians also knew about soap, but it's Romans who are the first one to provide a written recipe that's passed down throughout the ages. Not saying that the other tribes and clans and the other groups of early people didn't have recipes, but they've been lost to time. So now what they would do is they'd take goat fat and wood ashes and heat that. And the wood ashes are slightly basic, and that would produce their soap. They'd also take the goat fat and the lye and heat it to produce soap. Remember, lye is our sodium hydroxide. That you want the fat plus the base, and you would produce the soap. Lye has its origins in various different languages. There's a word for lye in Latin, in Greek, Old English, and Gaelic. Now, soap is actually a sodium and sometimes a potassium salt of a long chain carboxylic acid. So remember, a carboxylic acid is a group with C double bond O and OH. So we combined an alcohol with a carbonyl group, a ketone or aldehyde. And the long chain hydrocarbon is just a long alkyl chain of some kind with no real functional groups other than carbons. Now, I've shown an example of sodium palmate, which is a common soap we see. That it's, you see, we have the carboxylic acid, we turned it into a salt, so it's carboxylate, and we have C14 and a CH3 at the end. So we have 14 CH2 groups. So this is why it's a long chain hydrocarbon. The generalized formula is just CH3, CH2N, CO2, Na+. So the chain length can vary and still be a soap. Usually this N ranges between 8 and 16. Now, what makes soap so special is the opposing properties in here. We have a long hydrocarbon tail, as you can see here, and a polar ionic head up here. This gives it two properties. The hydrocarbon tail acts like gasoline, acts like mineral oil. It'll readily mix with and dissolve other hydrocarbons like fats and oils. The but it won't readily mix with water. Now, the carboxylate group, being ionic, is also highly polar. Now, ionic molecules tend to dissolve very well in water, but not want to mix in hydrocarbons. So we have what's called a polar head and a nonpolar tail. The polar head is very hydrophilic, which is Greek for water loving. And the tail is very hydrophobic, meaning water fearing. So the tail doesn't like water, but the head does. And so all detergents will contain some sort of hydrophobic and hydrophilic portions. As they mix with water, they will try to accommodate both of these portions. So when we mix this with water initially, it's going to align itself on the surface with the polar head sticking into the water and interacting with the water, and the nonpolar tail sticking and waving into the air because it's trying to get as far away from the water molecules as possible. With that in mind, this breaks up the nice tight cohesion that was normally in the water. So once we mix the detergent into the water, it's going to lower the surface tension. Now, a substance that will accumulate on the surface causing a sharp change, such as lowering the surface tension, is called a surface active agent, or often known as a surfactant. While there are some non-surfactants that can lower the surface tension, they typically won't have the same dramatic effect as a surfactant. So, for example, 1% soap can cause a 70% decrease in surface tension. Now, sodium hydroxide can also have an effect, but it takes 5% sodium hydroxide solution to increase the surface tension by 6%. So, barely an increase. While we have essentially the soap has a huge decrease for a little amount, and the lye has a very small increase considering how much it's needed. Now, all soaps, which are sodium carboxylates, are considered detergents, but not all detergents need to be soap. And all detergents are surfactants, but not all surfactants need to be detergents. But the fact we're going to look at soap and detergent and surfactant all together. So all that talks about is essentially what happens when I start to add soap. We break up the surface tension. Well, when I add too much soap, something strange starts to happen. We can no longer accommodate the soap on the surface, and so we form something known as a micelle that forms in the center of solution. A micelle is a submicroscopic globules or spheres of one substance distributed through another, usually a liquid. So this micelle is the glob of soap that's going to form up, so all the tails are in the center, all the heads are in the on the outside. Now this looks like just a circle right now, but you got to remember this is a sphere. This is the three-dimensional sphere where it's completely coated. All the heads are on the outside, all the tails are in the inside, keeping all that soap, the hydrophobic region, safe from the water. This will be well dispersed within the water, but it's not really truly dissolved. This actually forms a colloid. Now, a colloid is just a mixture of particles of one substance dispersed through another, where the particle range are somewhere between the diameter of 10 to the negative 7th or 10 to the negative 4th, between that range, which of centimeters. Before you start like, okay, so what does that actually mean? Well, you got to remember, most ions are about 10 to the negative 8th. So between somewhere like 10 times larger than an ion to several thousand times larger than an ion. So most ions are much smaller and it's going to be a solution. While there's no set cutoff for how big the the substance needs to be a colloid, there is a very easy way to tell. And that easy way is to the observation of the Tyndall effect. It was discovered by John Tyndall, and it's basically that a colloid, when you shine a light on it, it will cause a dispersion of a scattering of the light. This will cause a scattering of the light beam, allowing us to see the path. Now, I'll show you this effect in just a minute, but you can do this with milk. You drop a couple drops of milk into water and shine a light through it. You're going to see the beam of light. If you try to shine the light through just a normal glass of water, you won't see the light. Now, fog is an example of a colloid. That if you ever you see headlights through the fog, they don't appear really clear. You can actually see the beams penetrating as the water droplets disperse that fog. Now, you can see there's many different types of colloids that exist where solids, liquids, and gases are dissolved in each other. The only one that doesn't exist is a gas within a gas, because gases can mix 100%. They don't have to. Remember, they act like ideal gases. They don't have to separate. So when they mix 100%, they're essentially dissolved rather than dispersed. They don't clump up. So a gas dissolved in a liquid, it becomes a foam, like whipping cream or shaving cream. A gas dissolved in a solid would be like popcorn. A liquid dissolved in a gas would be like an aerosol, like fog. A liquid dissolved in a solid would be like a gel. Solid dispersed in a gas is another aerosol, like smoke. Many gemstones are solids dispersed in other solids. So we'll show you this Tyndall effect in just a second. This is an example of the Tyndall effect. You can see on the right we have no suspension, just liquid passes through. On the left we have some sort of suspension or colloid. You can see where that laser pointer is passing through as it's being scattered by the colloid suspended in solution. Now that we've talked about what is a soap, how do soaps actually work? They have three major purposes. One, they're going to decrease the surface tension. Two, they're going to dissolve the grease. And three, they're going to wick it away. The first thing is you need to decrease the surface tension of the water, because water will bead up. In order for water to clean, it needs to thoroughly wet a surface. Now, water will eventually wet most things, but you'll notice if you put water on something waxy, it'll bead up. You put this on a freshly waxed car, it's going to bead up and run right off. You see water on a rose petal, it's going to bead up because the surface tension of the water is very high. And the hydrophobic interaction between the wax and the water is going to want to minimize all contact between the water droplets and the surface. So it's going to bead up and not going to sink in as fast. So that's what happens initially with clothes. When you get it wet, it's going to bead up on the surface before it soaks in and soaks clothes completely. Well, the soap, when you add the detergent, is going to lower the surface tension so that water is going to spread out and soak in more thoroughly and faster. Once the soapy water is sunk in, it's going to be the soap is going to stick to the and form a micelle on the grease or the dirt, the grime. It's going to stick with the tails sticking into the grease and the heads poking out of the grease into the soapy water mixture. there's going to essentially link up and connect these two phases. We have the water phase and the grease phase. These two things that normally will not mix. We've essentially linked them up by forming a micelle between the two. At that point, agitation will help shake free this grease and grime. As you agitate it, it's already kind of being held on. The water pulls the soap, which pulls the grease. It yanks it off the fabric, and the grease starts to form small little globules, which then get encapsulated in micelles. So we form micelles sticking the grease right in the middle. Now, because these soap molecules are anionic, because they have a carboxylate, that's C double bond O, O minus, they are very negatively charged heads. Because they're negatively charged heads, these micelles are going to repel themselves from other micelles. They're going to stay far away. They're not going to bump into each other and get bigger. We're going to try to keep them apart. And because of that, we keep the grease from coalescing together into bigger micelles and keep them from redepositing on the fabric. So eventually, when the water goes down the drain, it pulls the micelles with it and drags the dirt and grime and grease out of the washing machine and into the drain, keeping your clothes clean. So that is how soap works. Well, how is soap actually formed? We talked about how they did it in ancient Rome, but how does we do it chemically? Well, the first thing we need to understand is, well, soap is formed through hydrolysis of an ester. The ester group is what happens when we combine the carboxylic acid with a alcohol group. Hydrolysis is simply the decomposition of a substance or conversion to another substance through the action of water. So remember our lysis when we talked about electrolysis, where we broke sun apart with electricity. Well, hydrolysis is to break sun apart with water. So the first thing we need to understand is how are esters formed. Well, carboxylic acid, like ethanoic acid, acetic acid, can mix with ethanol in the presence of an acid. Well, acetic acid is a acid. It's a very weak acid, so we need a stronger acid like HCl or sulfuric acid to catalyze this. But what happens is we form water and we replace the O carbon oxygen carbon bond, make a new carbon oxygen carbon bond to link these two together. And so that's how we form ethyl acetate, a standard ester. Well, all that's well and good, but how do we break them apart? Well, esters can easily be broken apart by acid and heat or base and heat. Well, if we do acid and heat, it just reverses the process and we get our carboxylic acid and our alcohol again. However, if we use base and heat, we get a product that's slightly different. We would get a sodium acetate and would get the ethanol. That essentially, instead of having that acid, we would be deprotonated and neutralized to form sodium acetate. Sodium acetate, which is essentially a soap. Not quite a long enough chain to be a proper soap, but a soap. And this process is called saponification, which is the hydrolysis of an ester carried out in the presence of a base. Now, the book doesn't talk about this, but saponification, the term is Latin for essentially sapon is soap, ification is the to make, so it's to make soap. Latin for to make soap, so saponification. Now, that's just a simple process, but how do we actually form fats? Well, to form this, we're going to have to attack triglycerides. Triglycerides are essentially fat or vegetable oil. Triglycerides is a combination of an ester that's formed from glycerol or glycerin, with either with an E or without an E at the end. But glycerol is essentially a 3-carbon triol, meaning 3 alcohol groups on this. And we form 3 fatty acids come together, fatty acids being the long chain hydrocarbon acids that are generated through the hydrolysis of fats. But as a long chain hydrocarbon acids form 3 different ester groups that combine there to form a triglyceride. I said they can all have different chain lengths. You could have caprylic acid, which is a 6-carbon chain. If I'm not mistaken, caprylic and capric acid probably come from are present in goat fat. Lauric acid, which is a 10-carbon chain. Myristic acid, palmitic acid, stearic acid, oleic acid. Oleic acid has a double bond in the middle. Linoleic acid has some double bonds in there as well. That these double bonds do things to the properties, but all of these fatty acids could be bound in different ratios to make different triglycerides. I'm not going to really give you any of the names because we don't need to know the names. Now, soaps made from that work really relatively well, but the bane of all soap is hard water. Hard water is water impregnated with minerals like calcium, magnesium, or iron. Now, sodium doesn't count. That's present in soft water. You can't ever have no minerals unless you're distilled. But if you have calcium, magnesium, or iron, you have hard water. What these do is, while the sodium salts of the fatty acids are highly soluble, the salts of calcium, magnesium, or iron are insoluble, meaning they precipitate as a solid. That the 2 molecules of soap come on and bind to the 2+ of calcium, the 2+ of magnesium, or 3 molecules bind to the 3+ of iron. And this forms a waxy, insoluble solid, sometimes called soap curd or soap scum. Now, the hard water will both waste soap because you'll lose some of the soap. It's going to consume some of it that you need for cleaning. But also the scum can then redeposit on clean clothes, dulling the color, making them gray. If you've ever had hard water in the shower, you have soap scum rings around the tub if you try to clean up. And then also this will cut down on sudsing. If you mix any calcium into like bubbly water, the suds just disappear right away. Now, there's several different solutions to solving this. One such solution is water softeners. So water softener, you have to install a very specialized tank that has a polymer. It'll have a storage bin for sodium chloride and a water flow regulator to keep so that we don't get too much water pressure and blow it out. But so what happens is the polymer has various anionic functional groups that can bind to cations. So the first thing you have to do is activate it by flushing it with highly concentrated sodium chloride salt water that flushes all the ions off the polymer. And then as your hard water flows in, it's going to knock off the sodium and bind more tightly to the anionic surface. So it's going to catch the calciums, the magnesiums, the iron, and the sodium is going to just flow right through and be displaced by it. So the water that comes out will be significantly softened. But every so often, you do have to replace, you have to refresh the resin. You have to refresh the polymer by flushing with more highly concentrated sodium to flush off all the hard minerals on there. But So this polymer is an example of an ion exchange resin. Now, the other method is using synthetic detergents, which were invented in the 1940s. That things like alkyl benzene sulfonate, where instead of the long chain hydrocarbon, it has a benzene group and a sulfate, that sulfonate, which is SO3 1 minus instead of the carboxylate. The idea is that the sulfonate is highly soluble with various calciums and magnesiums, that it's not going to precipitate in the same way. Now, while it's harder to put a sulfonate on a long fatty acid, it's relatively easy to put it on a benzene group, which is why we are doing such example. And because we're building this through chemistry rather than just a simple mixing of fat and base, we can actually kind of direct how we're making this and make different groups depending on the purpose, such as toothpaste. You can tailor it, the structure, to the need. Make some detergent. Essentially, toothpaste is an example of the detergent that cleans your teeth. Now, as you see, there's various anionic examples of detergents. Sodium carboxylate, we know about. We have the sodium alkyl benzene sulfonate, and we have a sodium alkyl sulfate. Sulfate. Those are examples of things that can be made. There are some cationic ones. Well, we'll talk about it in a minute. And there's non-ionic ones. The non-ionic ones like alkyl polyethoxylate, that we have a series of essentially ethers with an alcohol in the end, that these can act as detergents with the polar, or essentially non-polar tail and polar head without the charge. The non-ionic detergents are actually a little bit better at cleaning synthetic fabrics because of the ionic charge, and there's some other benefits for the non-ionic ones, but they probably don't work as well on as to disperse the oils. Now, the cationic ones, where they use the positively charged ammonium as our ionic head, are actually antiseptics. They can act as germicides. So they will kill bacteria. So using these detergents are useful for cleaning things. So it's often used in antiseptic soap and in mouthwash. That you're essentially using mouthwash, using the detergent to clean your teeth as well as kill all germs in there. I think that's because most bacteria are gram negative, meaning they have an anionic cell, and so these bind to the surface and help kill them. I could be wrong. But all these are examples of types of detergents. Now, we'll finish up real quick with what is actually in a box of detergent. So the number one ingredient, so if you're getting like a detergent like, a synthetic detergent, number one ingredient is our surfactant, or some sort of detergent of one kind or another, like sodium alkyl benzene sulfonate. Now, the anionic detergent is all well and good, but we're slowly moving towards more non-ionic detergents because, as we'll see in a minute, we need a lot less builders. We don't need to soften the water with non-ionic detergents because they're not going to bind to cations. The anion of the anionic binds to cations. The same way the cationic detergent wouldn't bind to the sodium or the calcium, so we don't need to worry about that. The non-ionic doesn't bind to anything, bind to any cation or anion, so they don't have to use as much. We don't have to use as much extra stuff. And so that will keep us a little bit safer, and it's maybe a little bit better for the environment. But okay, the number two ingredient on most of these are builders. The builder's job is to essentially soften the water and help make our surfactant work better. One of the common builders was sodium tripolyphosphate, which was has very low cost, very low toxicity, and it binds very firmly to the heavy metal, the hard water. But the problem is, it is a very good nutrient for algae. So as it goes down the drain, gets into our lakes, gets into our streams, it helps breed algae by the boatloads. And when we form these algae blooms on the surface of these lakes and streams, they can completely cover the surface and essentially smother all the oxygen and prevent any oxygen exchange. So below the surface becomes an oxygen dead zone, and that tends to kill all the marine life. So you may have heard of algae blooms in the Gulf of Mexico, creating dead zones in there where there's no fish can live. These algae blooms essentially suck all the life by sucking up all the oxygen and then preventing oxygen from dissolving back into the water. So phosphates are now banned in many states. So another thing they use is microporous zeolites. Zeolites are just aluminosilicate minerals that can act as an ion exchange resin and bind to the hard water. So mixing those in to help soften the water a bit so that the sodium alkyl benzene sulfonate, even though they have a very high solubility in calcium and magnesium, it'll make them work a little bit better. Now, number 3 ingredient is the stupidest of all. It's a filler. Sodium sulfate is the most common filler. The number 1 reason it was added is to provide bulk to the detergent. So the consumer thought they were getting more bang for their buck. I wanted to get the most amount of detergent I could for my money. Well, you had a lot more filler in there. You don't need nearly as much. So they did that. But it also adds and helps the solid pour a little more freely. So it does have some use. But as we're kind of moving towards more environmentally friendly, the amount of fillers dropped from like 35% to between 10% and 0% filler. So we don't really need this to make the detergent work. Now they've added corrosion inhibitors. That's essentially to protect the washer parts and prevent them from rusting as they're agitating your clothes. They have suspension agents that essentially just to add and help keep the grease suspended and keep them from redepositing, since it's not the same, not maybe as great of a micelle as you would with the sodium carboxylates. You have various enzymes sometimes mixed in to remove those hard to get stains like grass and blood, break down the proteins. You have bleaches that essentially oxidize the molecule to remove the stains and make them fade. You have optical whiteners, which is like a dye, an organic thing that sticks on the molecule and makes the whites shine a little bit brighter. It doesn't actually clean. What it does is it makes the UV light, which is the light that we can't see that gives us the sunburns and the skin cancer, absorb and produce a slightly blue tint that makes the whites pop that much higher. And then we have fragrances and coloring agents to try to just make the clothes smell nicer and look prettier. All these are in the typical box of detergent, or at least solid detergent. Now, finish off. We need to do our writing prompt, our discussion prompt. So we need 150 words. 150 words. If you've ever had water in your gas tank, you've probably had to add something like heat or iso heat to help remove the water from the bottom of the tank. Well, heat is essentially methanol, which is CH3OH, an alcohol, a 1-carbon alcohol chain, which you should, by organic standards, know what that is. CH3OH. Isoheat is just isopropanol or rubbing alcohol, isopropyl alcohol. It's a 3-carbon chain with the alcohol in the center carbon on the second carbon. So these are the two main components in heat and isoheat. Now, using terminology from this chapter, or surfactant chapter, describe how they would work as you add them to a gas tank. Describe what would happen as we remove the water from the bottom of the tank. Could then answer the question, could a synthetic detergent be used as well? Which, if so, what synthetic detergent would you use? And then finally, describe what is the most likely products that would come out of the gas tank when you burn these guys, whether heat, isoheat, or your synthetic detergent. What would come out? To help you remember, when you combust something, the elements turn into various oxides. If you burn carbon, carbon goes to carbon dioxide. When you burn hydrogen, we form H2O, which is water. So what other products would you expect to see as you burn these guys? So answer that in a prompt, and that will be what I require for you for this chapter. I'll see you for the next chapter.